Echoes of creation, a faint whisper from the Big Bang. Imagine listening to the faintest whisper, a murmur from the very dawn of time. That's essentially what astronomers do when they study the cosmic microwave background radiation, often shortened to CMB. This faint afterglow permeates the entire universe and serves as a direct relic of the Big Bang, the event that marked the beginning of everything we observe today. By studying this ancient light, we can peer back in time to an era when the universe was just a baby, a mere 380,000 years old. The CMB provides us with a snapshot of this early period, offering invaluable clues about the universe's composition, structure, and evolution. It's a cosmic time capsule, holding secrets to our very existence. The universe's fiery beginning, a sea of light. In the immediate aftermath of the Big Bang, the universe was an extremely hot and dense soup of elementary particles. Light couldn't travel freely in this chaotic environment. Photons, the particles that make up light, were constantly colliding with charged particles like protons and electrons, getting scattered in all directions. As the universe expanded, it also cooled down. Eventually, the temperature dropped enough for protons and electrons to combine and form neutral hydrogen atoms. This transition, known as recombination, marked a pivotal moment in cosmic history. With fewer charged particles to impede their journey, photons were finally free to travel unimpeded across the cosmos. This first burst of light, released when the universe was about 380,000 years old, is what we now detect as the cosmic microwave background. Cosmic whispers, detecting the afterglow of creation. The CMB is essentially the leftover heat from the Big Bang, stretched out over billions of years of cosmic expansion. It's not visible to the naked eye because its wavelength has been stretched from the visible light spectrum into the microwave range. In 1964, two American astronomers, Arno Penzias and Robert Wilson, stumbled upon the CMB while working on a new antenna at Bell Telephone Laboratories. They initially thought the faint uniform signal they detected was interference from their equipment or even pigeon droppings. However, after meticulously eliminating all other possibilities, they realized they had discovered something profound, the afterglow of the Big Bang. This serendipitous discovery revolutionized our understanding of the universe and earned Penzias and Wilson the Nobel Prize in Physics in 1978. Ripples in the fabric deciphering the CMB's secrets. While the CMB appears remarkably uniform, it does contain tiny temperature fluctuations on the order of a few millionths of a degree. These minute variations are like cosmic fingerprints, each one telling a story about the early universe. These fluctuations, often referred to as anisotropies, are incredibly significant. They provide a snapshot of the universe just 380,000 years after the Big Bang, a time when the universe was still in its infancy. They represent the seeds of the large-scale structure of the universe we observe today. These tiny differences in temperature and density eventually led to the formation of galaxies, stars, and clusters. These minute variations in temperature correspond to regions of slightly different densities in the early universe. These density differences were crucial in shaping the universe's evolution. Over billions of years, gravity amplified these density differences, pulling in more and more matter to form the web-like structure of galaxies and galaxy clusters we see today. This cosmic dance of matter and gravity is what has shaped the universe's vast and intricate structure. By studying the pattern and intensity of these temperature fluctuations, cosmologists can extract a wealth of information about the universe's age, composition, and geometry. This data helps us understand not just where we come from, but also the fundamental laws that govern the cosmos. It's like looking at a baby picture of the universe and being able to predict its future growth and development. By analyzing these ancient signals, scientists can piece together the story of the universe from its earliest moments to its current state, and even make predictions about its future. Serendipity and static, the accidental discovery of a lifetime. In the 1940s, physicists Ralph Alpher and Robert Herman, working with George Gamow, had predicted the existence of a cosmic background radiation as a consequence of the Big Bang model. This was a groundbreaking theory that suggested the universe was filled with a faint glow from its very inception. They even estimated its temperature to be around 5 Kelvin, which is minus 450 degrees Fahrenheit. This prediction was based on their calculations of how the universe would have cooled down over billions of years. Fast forward to 1964, a time when the scientific community was buzzing with new discoveries and technological advancements. Arno Penzias and Robert Wilson at Bell Labs were puzzled by a persistent hiss in their sensitive microwave antenna. This noise was a constant, no matter what they tried. They tried everything to eliminate the noise. They recalibrated instruments, checked for equipment malfunctions, and even evicted a family of pigeons that had nested in the antenna. The annoying hiss persisted, defying all their efforts. Unbeknownst to them, they had stumbled upon the very echo of creation predicted by Alpha, Hermann, and Gamow. This was a monumental discovery that would change our understanding of the universe. The faint signal, measuring just a few degrees above absolute zero, was the elusive cosmic microwave background radiation. This discovery provided the strongest evidence yet for the Big Bang theory, confirming that the universe had indeed begun with a massive explosion. A universe unveiled, the CMB and the Big Bang's legacy. The story of our universe is written in the light of the stars and the echoes of the Big Bang. The discovery of the cosmic microwave background, or CMB, provided the most compelling evidence yet for the Big Bang theory, a theory that describes the birth and expansion of our universe from a singular, incredibly hot and dense point. The remarkable agreement between the predicted temperature of the CMB and the actual temperature measured by Penzias and Wilson in 1965 solidified the Big Bang as the leading explanation for the origin of the universe. Their groundbreaking work earned them the Nobel Prize in Physics. Furthermore, the CMB's properties provided insights into the universe's composition, revealing a cosmic recipe that has fascinated scientists for decades. The pattern of temperature fluctuations indicated that the universe is composed of about 73% dark energy, 23% dark matter, and only about 4% ordinary matter, the stuff that makes up stars, planets, and us. This tiny fraction of ordinary matter is what forms the galaxies, stars, planets, and all known life. The discovery of the CMB ushered in a new era of precision cosmology, allowing scientists to measure the universe with unprecedented accuracy. It allowed scientists to test and refine models of the early universe and gain a deeper understanding of its evolution. This discovery has paved the way for future explorations, helping us to unravel the mysteries of the cosmos and our place within it. A universe inflated, solving the horizon problem. One of the puzzles that the CMB helped solve is the horizon problem. The CMB is remarkably uniform in temperature in all directions. This uniformity is puzzling because, according to the standard Big Bang model, regions of the early universe that were vastly separated shouldn't have had enough time to reach thermal equilibrium, meaning they shouldn't have had the same temperature. To explain this uniformity, physicists proposed a theory called inflation. Inflation posits that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. This rapid expansion would have smoothed out any initial temperature differences and stretched quantum fluctuations to cosmological scales, seeding the temperature anisotropies we observe in the CMB. Sharpening the image modern missions and the CMB. Since the serendipitous discovery of the CMB, astronomers have launched dedicated space missions to map it in greater detail. The Cosmic Background Explorer, or COBE satellite, launched in 1989, provided the first detailed all-sky map of the CMB, confirming the temperature fluctuations predicted by inflation. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, produced even more precise maps of the CMB, refining our understanding of the universe's age, composition, and geometry. The Planck satellite, launched in 2009, provided the most detailed and accurate measurements of the CMB to date. Planck's observations have further constrained cosmological parameters and provided new insights into the early universe. The future of cosmology, the enduring legacy of the CMB. The cosmic microwave background radiation remains a treasure trove of information for cosmologists. Future missions and observations promise to reveal even more about the universe's earliest moments and its evolution. Scientists are particularly interested in searching for signs of primordial gravitational waves. ripples in space-time generated during inflation. Detecting these waves would provide further support for inflation and offer insights into the universe's energy scale during that epoch. The CMB is a testament to the power of scientific inquiry and the ingenuity of astronomers. It's a faint echo from the dawn of time, whispering secrets about the universe's birth, evolution, and ultimate fate. By listening carefully to this ancient light, we continue to unravel the mysteries of our cosmos and our place within it.